Thermal processes are essential for understanding how energy is transferred and how matter behaves at the molecular level. In this section, we'll explore the key principles that govern heat energy transfer and how it impacts the properties of solids, liquids, and gases. Understanding thermal processes is crucial for fields like engineering, physics, and chemistry, as they underpin many fundamental phenomena in the physical world. By the end of this section, you'll have a deeper grasp of the mechanisms behind heat transfer and the ways in which temperature and energy can transform the state and behavior of different materials. Let's dive in and unpack the fascinating world of thermal processes. Heat naturally flows from hotter to cooler areas, driven by the tendency for thermal energy to balance out across different regions. In solids, heat is transferred through the vibration and collision of atoms and molecules. This molecular motion allows heat to spread throughout the material. As atoms and molecules vibrate, they exchange kinetic energy through collisions. This conduction process gradually moves thermal energy from hotter to cooler parts of the solid. The transfer of thermal energy at the molecular level is a key mechanism for how heat is distributed within solid materials. Heat naturally flows from hotter to cooler regions due to temperature differences. This fundamental principle drives many thermal processes we encounter daily and in industry. The temperature difference causes energy to move from the hotter area to the cooler area until equilibrium is reached. Understanding heat flow behavior between regions of varying temps is crucial for designing effective heating, cooling, and insulation systems. It also helps optimize industrial processes and improve energy efficiency. The key heat flow principles covered on this slide are temperature gradient, direction of heat flow, and energy transfer. Heat always flows from regions of higher temperature to regions of lower temperature. This temperature difference drives the transfer of thermal energy. The direction of heat flow is determined by the temperature gradient, with heat moving spontaneously from hotter to cooler areas until thermal equilibrium is reached. As heat flows, thermal energy is transferred from the hotter substance to the cooler one, raising the temperature of the cooler substance and lowering the temperature of the hotter one. The illustrations on this slide help visualize these fundamental heat flow concepts. Solid materials transfer energy at the molecular level through the vibration of atoms around their fixed positions. As atoms vibrate, they transfer their kinetic energy to neighboring atoms, allowing heat to flow through the material by conduction. This process, known as phonon transport, is the dominant mechanism for heat transfer in solids. The oscillations of atoms in a solid lattice create a flow of thermal energy, with the vibration energy being passed from one atom to the next. This allows solids to efficiently conduct heat, in contrast to gases where molecules move independently with limited energy transfer between them. Solid materials are made up of tightly packed atoms that are constantly vibrating around their fixed positions due to the thermal energy present in the solid. As these atoms vibrate, they collide with their neighboring atoms, transferring kinetic energy through a process called conduction, which is the primary mode of heat transfer in solids. The efficiency of conduction in a solid depends on the material's crystalline structure and the strength of the atomic bonds. Materials with a well-organized crystal lattice and strong bonds, like metals, tend to be better thermal conductors. Conduction pathways in solids allow for the effective transfer of heat energy through the vibration and collision of atoms. Solid materials have atoms that are tightly packed and vibrate around fixed positions. This vibration is due to the thermal energy within the solid, causing the atoms to oscillate back and forth. The amplitude of these vibrations increases as the temperature of the solid rises, indicating higher kinetic energy among the atoms. The kinetic energy of atoms in a solid is important for understanding heat transfer and thermal conductivity. As the atoms vibrate, they can transfer energy to neighboring atoms through collisions, enabling heat flow within the solid. Solid materials are made up of tightly packed atoms and molecules that vibrate in fixed positions. This vibration allows energy to be transferred through the solid via conduction. The vibrations are passed from one particle to the next. The increased kinetic energy of the vibrating particles at higher temperatures causes them to vibrate more rapidly. This higher energy motion is then transferred to neighboring particles, allowing heat to flow through the solid material. The crystalline structure and atomic bonds within a solid provide pathways for heat energy to be conducted through the material. Substances with stronger atomic bonds, like metals, tend to be better heat conductors compared to materials with weaker bonds, like plastics. Fluids like air and water expand when heated and become less dense. Conversely, fluids contract and become more dense when cooled. These differences in density create convection currents within the fluid. Warmer, less dense regions rise, while cooler, denser regions sink. This continuous circulation of the fluid is called a convection current. Convection currents are a key mechanism for heat transfer in liquids and gases. Understanding convection is important for things like weather patterns, ocean currents, and heating/cooling systems. Fluids like air and water can undergo convection currents due to changes in density. As a fluid is heated, its molecules gain kinetic energy and spread out, making the fluid less dense. The lower density heated fluid then rises, while the cooler, denser fluid around it sinks. This creates a circular flow pattern known as a convection current. The motion of these convection currents helps transfer thermal energy through the fluid, carrying heat from hotter to cooler regions. This circulation and heat transfer allows for more even temperature distribution in the fluid. Convection is the transfer of heat through the movement of a fluid, like air or water. When a fluid is heated, the molecules move faster, causing the fluid to expand and become less dense. The warmer, less dense fluid will rise upwards, creating a convection current. The cooler, denser fluid surrounding the warmer fluid will sink downwards. This creates a continuous circulation pattern, with the warmer fluid rising and the cooler fluid descending. This process of heat transfer through fluid movement is essential in many natural and man-made systems. Examples include atmospheric weather patterns and heating/cooling systems in buildings. Convection currents are the circulation of fluids like air or water, driven by differences in density. When a fluid is heated, its density decreases, causing it to rise and create a convection current. As the heated fluid rises, cooler, denser fluid rushes in to replace it, setting up a continuous circulation pattern. These convection currents play a crucial role in heat transfer, weather patterns, and many industrial and natural processes. The strength and direction of the currents are influenced by factors like temperature gradient, fluid viscosity, and external forces like gravity. The illustration on the slide shows an example of how convection currents work, with hot and cold air or water moving in a circular pattern. Radiant energy is transferred through electromagnetic waves without needing a physical medium. Darker surfaces tend to absorb more of this radiant energy, while lighter surfaces reflect more. The amount of radiant energy a body can emit or absorb is directly proportional to its surface area. Larger surfaces can transfer energy at a higher rate. Energy can be transferred through radiation without the need for a material medium. Radiant energy is transmitted as electromagnetic waves, which can take many forms like visible light, infrared, and ultraviolet. When an object emits radiant energy, it directly transfers that energy to its surroundings, allowing for rapid and efficient heat transfer over a wide range of distances. This is different from conduction and convection, which require a physical medium to transfer energy. Radiant energy, like light and heat, travels through space as electromagnetic waves. This type of energy transfer doesn't require a physical medium. It can travel through a vacuum at the speed of light. The oscillating electric and magnetic fields from the source interact with the receiving object, causing it to absorb or reflect the energy. The rate and efficiency of this process depends on factors like the surface properties and temperature of the objects involved. Unlike conduction and convection, radiant energy transfer doesn't need a physical medium to propagate. The color of a surface plays a key role in its ability to absorb or reflect radiant energy. Darker surfaces like black or dark colors tend to absorb more radiation, while lighter surfaces like white or reflective materials reflect more. The texture of a surface can also impact its radiant energy absorption and emission. Rough, matte surfaces are generally better absorbers of radiation, while smooth, glossy surfaces tend to reflect more. A surface's emissivity, or its ability to emit radiant energy, is influenced by its color and texture. Surfaces with high emissivity, like those that are dark and matte, will emit more thermal radiation. Surfaces with low emissivity, like light and glossy materials, will emit less thermal radiation. The color and texture of a surface play a crucial role in its ability to absorb thermal radiation. Darker, rougher surfaces have a higher absorption rate compared to lighter, smoother surfaces. When thermal radiation in the form of photons hits a surface, the photons can be absorbed, reflected, or transmitted. Darker surfaces tend to absorb more photons, converting the energy into heat, while lighter surfaces reflect a larger portion of the radiation. This principle has important implications for things like energy efficiency, heating, and cooling. Lighter, smoother surfaces have higher reflectivity, meaning they bounce back more of the radiant energy that hits them. In contrast, darker, rougher surfaces absorb more of the incident energy. Highly polished, even surfaces reflect light efficiently, creating a mirror-like effect. Rougher textures tend to scatter the light in different directions, reducing the reflective properties. Light colors, especially white, have high reflectivity compared to darker shades. Bright, white surfaces are often used to maximize the reflection of light and heat in applications like building insulation and energy-efficient design. Lighter, smoother surfaces have higher reflectivity, meaning they bounce back more of the radiant energy that hits them. In contrast, darker, rougher surfaces absorb more of the incident energy. Highly polished, even surfaces reflect light efficiently, creating a mirror-like effect. Rougher textures tend to scatter the light in different directions, reducing the reflective properties. Light colors, especially white, have high reflectivity compared to darker shades. Bright, white surfaces are often used to maximize the reflection of light and heat in applications like building insulation and energy-efficient design. Larger surface area means more energy radiated. A surface 4 times larger radiates 4 times more energy at the same temperature. Doubling the surface area results in a 200% increase in the amount of radiant energy emitted. This principle is crucial for understanding heat transfer through radiation and designing efficient heating/cooling systems. The relationship between surface area and radiant energy emission is direct and proportional. Larger surfaces radiate significantly more energy than smaller ones at the same temperature. Heating, ventilation, and air conditioning (HVAC) systems rely on thermal processes to regulate indoor temperatures and maintain comfortable environments. Thermal mechanisms like conduction, convection, and radiation are essential for various cooking methods, enabling the transformation of raw ingredients into cooked dishes. Thermal processes are fundamental to power generation, from traditional fossil fuel-based plants to renewable energy sources like solar thermal and geothermal systems, as they enable the conversion of heat into mechanical or electrical energy. Thermal processes are the foundation for heating, ventilation, and air conditioning (HVAC) systems, which regulate indoor temperatures for comfort and energy efficiency. Effective insulation materials and design leverage thermal processes to minimize unwanted heat transfer, improving the energy efficiency of buildings and appliances. Thermal processes such as conduction, convection, and radiation are essential for cooking, baking, and other food preparation techniques that transform raw ingredients into delicious meals. Thermal processes play a critical role in various industrial applications, including material processing, chemical reactions, and power generation, driving efficiency and productivity. Central heating and cooling systems are the backbone of climate control in many homes and buildings. These integrated systems use a furnace or heat pump to regulate air temperature and an air conditioning unit to provide cooling. The systems circulate air through a network of ducts and vents throughout the building. Central HVAC systems offer a comprehensive solution for maintaining comfortable indoor temperatures year-round. Advanced smart thermostats give users precise control over their heating and cooling. These intelligent devices allow programming schedules, monitoring energy usage, and making remote adjustments from smartphones. Smart thermostats help optimize HVAC efficiency and reduce utility costs for homeowners and building managers. Geothermal heating and cooling systems harness stable underground temperatures to provide efficient climate control. By transferring heat to or from the earth, These systems can drastically reduce energy consumption and greenhouse gas emissions compared to traditional HVAC options. Geothermal systems offer a sustainable, cost-effective alternative to conventional heating and cooling technologies. Effective insulation materials like fiberglass, foam, and cellulose create barriers that slow down heat transfer, helping maintain desired temperatures and reduce energy costs for heating and cooling. Heat can be transferred through conduction, convection, and radiation. Insulation materials work by reducing heat flow through these pathways, trapping warmth or coolness inside the insulated space. The R value measures an insulation material's resistance to heat flow. Higher R values indicate better insulating properties. Choosing the right R value for a building's location and climate is crucial for energy efficiency and comfort. Cooking and food preparation rely heavily on various thermal processes to transform ingredients and create delicious, nutritious meals. Chefs and home cooks utilize all three modes of heat transfer, conduction, convection, and radiation, to achieve the desired cooking effects. Accurate temperature regulation is crucial for successful cooking, as the degree of heat can significantly impact the texture, flavor, and nutritional content of the food. Advanced kitchen appliances and thermometers allow for precise control and monitoring of temperatures throughout the cooking process. Industrial processes rely on advanced thermal technologies to optimize efficiency and productivity. Thermal processes are used to heat, melt, and shape materials at various stages of industrial production. Innovative thermal management systems in industrial facilities can capture and recycle waste heat. Many industries require precise temperature control during manufacturing to ensure product quality and consistency. Thermal power plants are a major source of electricity generation, converting the thermal energy of fuels like coal, natural gas, or nuclear fission into mechanical energy to drive generators. These plants use boilers, turbines, and other equipment to efficiently harness the heat and produce electricity on a large scale. Hydroelectric power plants leverage the kinetic energy of flowing water to spin turbines and generate electricity. Dams and reservoirs help control water flow and increase the potential energy. The mechanical energy from the spinning turbines is then converted into electrical power through generators. Wind power is a renewable, clean energy source that harnesses the kinetic energy of wind to rotate turbine blades and drive generators. Wind farms are becoming increasingly important in the global effort to reduce fossil fuel consumption and transition to more sustainable energy sources. The Earth's climate and environmental systems are heavily influenced by thermal processes like conduction, convection, and radiation. These thermal processes drive global air and ocean currents, which in turn shape weather patterns and long-term climate trends. The greenhouse effect, where heat-trapping gases absorb and re-emit infrared radiation, is a key thermal process behind global temperature changes. Understanding and managing these thermal dynamics is crucial for addressing climate change and its environmental impacts. Thermal processes are also central to many renewable energy technologies like solar, geothermal, and biofuels. Harnessing the natural flow of heat on Earth can provide sustainable and eco-friendly energy solutions. Changes in temperature and precipitation patterns due to thermal processes can disrupt ecosystems and biodiversity, leading to species migration and extinction. Careful management of these thermal implications is required to maintain the delicate balance of natural habitats. Biological systems rely on complex mechanisms to maintain an optimal internal temperature. Metabolic processes generate heat within the body. Heat is lost through evaporation, convection, and radiation. The body regulates temperature through autonomic responses like sweating to cool down and shivering to warm up. All of this is coordinated by the brain's temperature control center. Understanding these thermoregulation principles is crucial for applications like athletic performance, workplace safety, and medical treatments. Monitoring and optimizing an organism's thermal balance can improve health, productivity, and overall functioning. Temperature scales like Celsius, Fahrenheit, and Kelvin allow us to precisely quantify and compare thermal energy across different contexts and applications. Calorimetry is the scientific process of measuring the heat energy absorbed or released during chemical or physical changes. It helps determine a system's specific heat capacity and enthalpy. Thermal imaging cameras detect infrared radiation and translate it into visual images that represent temperature variations across a surface or scene. This enables non-invasive measurement of heat distribution and energy flows. The Celsius scale is based on the freezing and boiling points of water, which are 0 degrees Celsius and 100 degrees Celsius respectively at standard atmospheric pressure. This is the most widely used temperature scale worldwide for everyday use. The Fahrenheit scale is primarily used in the United States. It is based on the freezing point of a brine solution, 0 degrees Fahrenheit, and the average human body temperature, 96 degrees Fahrenheit. The Kelvin scale is the base unit of temperature in the International System of Units, SI. It is based on absolute zero, the coldest theoretical temperature, which is minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. Kelvin is used in scientific and technical applications. All three scales are important to understand as they are used in different contexts and regions. Being able to convert between them is a useful skill. Specific heat capacity is the amount of energy needed to raise the temperature of a substance by 1 degree Celsius. This varies depending on the material's chemical composition and molecular structure. Thermal conductivity is a measure of how well a material can conduct heat. Materials with high thermal conductivity, like metals, allow heat to flow more easily than those with low thermal conductivity, like insulation. Calorimetry is the measurement of heat during a chemical reaction or physical change. Calorimetry allows us to determine the specific heat capacity and thermal conductivity of different materials by precisely measuring the heat absorbed or released. Calorimetry is the scientific process of measuring the heat of chemical reactions or physical changes. It involves using a calorimeter device to measure the energy released or absorbed during a process. The heat of fusion is the energy required to change a substance from solid to liquid state. The heat of vaporization is the energy needed to change a liquid to a gas. By measuring factors like temperature changes, mass, and specific heat capacity, scientists can calculate the energy changes in a system. These calorimetry calculations help us understand the thermodynamics of a process. Thermal expansion and contraction refer to how materials change size and volume due to temperature changes. As temperature increases, atoms and molecules gain kinetic energy and vibrate more, causing the material to expand. Conversely, when temperature decreases, atoms and molecules slow down, resulting in the material contracting. This phenomenon is observed in solids, liquids, and gases and has important practical applications in engineering, construction, and scientific instrumentation. Understanding and accounting for thermal expansion/contraction is crucial for designing structures, machinery, and devices that can withstand temperature fluctuations without issues. The diagram on the right illustrates this process, showing a metal rod expanding and contracting as temperature increases and decreases. Thermal imaging technologies like infrared cameras can detect and visualize heat signatures, creating detailed thermal maps to identify temperature variations. Thermographic analysis uses thermal imaging to assess the condition and performance of systems, structures, and equipment, enabling predictive maintenance and energy efficiency optimization. In the medical field, thermal imaging has applications in early detection of breast cancer, monitoring of inflammatory conditions, and assessment of blood circulation, providing a non-invasive diagnostic tool. Beyond infrared cameras, advanced thermal sensors can measure temperature, heat flux, and other thermal properties with high precision, critical for monitoring and controlling industrial processes, building automation, and environmental monitoring. The fundamental laws of thermodynamics state that energy can neither be created nor destroyed, but only transformed from one form to another. This principle of conservation of energy is a critical foundation for understanding and modeling thermal processes. Computational fluid dynamics, CFD, allows us to create advanced models and simulations to accurately predict the behavior of fluids and heat transfer in complex thermal systems. Using CFD, we can optimize the design and efficiency of these thermal systems. Finite element analysis, FEA, techniques can model the thermal response of solid materials, structures, and components. FEA enables us to predict thermal stresses, deformations, and potential failure modes in these systems. Creating virtual digital twins of physical thermal systems allows for real-time monitoring, predictive maintenance, and continuous optimization through integrated simulations. Digital twins provide a powerful tool for understanding and improving the performance of our thermal processes. Thermal processes involve the conversion of various forms of energy, including heat, work, and electricity. The fundamental principle of energy conservation dictates that energy can neither be created nor destroyed, but rather transformed from one form to another. Improving the efficiency of thermal systems is crucial to maximizing energy utilization and minimizing waste. By analyzing the flow of energy and identifying areas of loss, engineers can implement strategies to optimize system performance and reduce environmental impact. The laws of thermodynamics, particularly the first law, energy conservation, and the second law, entropy increase, govern the behavior of thermal systems. Understanding these principles is essential for designing and operating efficient, sustainable thermal processes. Thermal processes are crucial for many industries, and improving their efficiency can have a significant impact on energy consumption and environmental impact. Advanced HVAC systems with features like heat exchangers, smart controls, and high-performance materials can significantly enhance energy efficiency, leading to lower operating costs and a smaller carbon footprint. Thermal imaging technology allows for the precise identification of heat loss, inefficient components, and potential issues in thermal systems, enabling engineers to optimize performance and minimize energy waste. Incorporating high-performance insulation and optimizing insulation strategies can substantially improve the efficiency of thermal processes by reducing heat transfer, leading to significant energy savings in both heating and cooling applications. The environmental impact of many thermal processes is significant, including greenhouse gas emissions, air pollution, and depletion of natural resources. This is an important challenge we need to address. Achieving high energy efficiency in thermal processes can be difficult, as some heat is always lost to the surrounding environment. But improving insulation, process optimization, and utilizing waste heat recovery can help improve efficiency. The materials used in thermal systems must be able to withstand extreme conditions like high temperatures and pressures. Finding cost-effective and durable materials that can reliably perform under these demands is an ongoing challenge. Overall, the environmental, energy, and material constraints pose significant challenges that need to be overcome in order to improve the sustainability and performance of thermal processes. Thermal processes have significant environmental impacts, particularly through greenhouse gas emissions. Optimizing energy efficiency and exploring cleaner energy sources are crucial to reducing the carbon footprint. Capturing and repurposing waste heat can improve overall system efficiency and reduce energy consumption. Technologies like cogeneration, heat exchangers, and thermal energy storage can help recover waste heat. The selection of materials used in thermal processes can impact sustainability. Exploring renewable, recyclable, or biodegradable materials is important. Implementing circular economy principles, such as reusing, repairing, and recycling components, can reduce waste and resource depletion. Advanced thermal imaging technologies can provide highly detailed visualization of heat transfer, allowing us to identify problem areas and optimize energy usage across a wide range of industrial and scientific applications. Nanotechnology is enabling the development of innovative insulation materials with unique thermal properties. These can be integrated into buildings, appliances, and industrial equipment to dramatically improve energy efficiency. Smart home and building technologies, including sensors, AI algorithms, and connected devices, are enabling more intelligent and adaptive thermal management systems. These systems can optimize temperature, airflow, and energy use based on factors like occupancy, weather, and other real-time conditions. We've covered a lot of ground in this presentation on the fundamental principles and applications of thermal processes. The key takeaways are the importance of understanding temperature gradients, the molecular dynamics of heat transfer in solids, the role of density changes in fluid convection, and the unique characteristics of radiative heat transfer. Applying these insights can lead to more efficient and sustainable thermal systems, which has benefits across industries, homes, and the environment. These core thermal principles are essential for designing and optimizing a wide range of practical applications that harness the power of heat. By deeply understanding these mechanisms, we can develop innovative solutions that improve energy efficiency, reduce environmental impact, and unlock new possibilities. The knowledge we've covered today provides a strong foundation for continuing to push the boundaries of thermal technology and engineering.